Hello! In this video, we are going to prove the following theorem. If A is a finite set whose cardinality is n, then the power set of A is finite, and its cardinality is 2 to the power of n. Okay, now before we get into proving this, let's first remind ourselves of some things. Given n is an integer greater than or equal to 0, we let in be the set of integers between 1 and n. So in particular, I0 is empty. So now our definition of a finite set is as follows. We say that a set A is finite if there exists an integer n greater than or equal to 0 such that there is a bijection from in to A. Now it turns out if there is an integer n greater than or equal to 0 such that this is true, then this integer n is unique. And we denote the unique integer n greater than or equal to 0 that satisfies this condition like this. And we call this the cardinality of A. Otherwise, we say that A is infinite. So now, here are some properties of finite sets that we are going to be using. So first, a set A is finite with cardinality 0 if and only if A is the empty set. A set A is finite with cardinality 1 if and only if A is a singleton set. Given A and B are finite and disjoint sets, then the union of A and B is finite, and the cardinality of the union of A and B is equal to the cardinality of A plus the cardinality of B. Given A and B are finite sets, with B a subset of A, then A set minus B is finite, and the cardinality of A set minus B is equal to the cardinality of A minus the cardinality of B. Given A and B are sets where A is finite, then there is a bijection from A to B, if and only if B is finite with the same cardinality as A. Now, we are going to be using a particular instance of this result right here, and that is the following. Given A is a finite set and x0 is an element of A, then A set minus x0 is finite, and the cardinality of A set minus x0 is equal to the cardinality of A minus 1. Okay, so now let's get into proving this theorem. Now, to prove this, we are going to be using induction on the cardinality of A. More precisely, we are going to be using induction to prove the following statement. We are going to use induction to show for every integer n greater than or equal to 0, we have for every finite set A with cardinality n, the power set of A is finite, and the cardinality of the power set of A is equal to 2 to the power of n. Okay, so let's start with the base case. In the base case, we are trying to prove that this is true in the case where n is equal to 0. So we're trying to prove for every finite set A with cardinality 0, the power set of A is finite, and the cardinality of the power set of A is equal to 2 to the power of 0. So to prove that, let's give ourselves an arbitrary finite set A with cardinality 0. Well then, we know that A is the empty set. So the power set of A is equal to the power set of the empty set. But what is the power set of the empty set? The power set of the empty set is the singleton set of the empty set. But why is this true? Well, we know that the empty set is a subset of every set, So the empty set is a subset of the empty set, and therefore the empty set is an element of the power set of the empty set. But how do we know that the empty set is the only element of the power set of the empty set? Well, if we consider an arbitrary element of the power set of the empty set, so if S is an arbitrary element of the power set of the empty set, then this means S is a subset of the empty set. But remember, the empty set is a subset of every set. So in particular, the empty set is a subset of S. So because S is a subset of the empty set, and the empty set is a subset of S, these two inclusions imply that S must be equal to the empty set. So this shows if we consider an arbitrary element of the power set of the empty set, it must be the empty set itself. So that shows that the empty set is the only element of the power set of the empty set. And so the power set of the empty set is the singleton set of the empty set. But singleton sets are finite sets with cardinality 1. So this shows us that the power set of A is finite and its cardinality is 1. And 1 is equal to 2 to the power of 0. And so this completes the base case. We have shown if A is any finite set with cardinality 0, then the power set of A is finite and its cardinality is 2 to the power of 0. So this completes the base case. Now let's move on to the induction step. In the induction step, we give ourselves an arbitrary integer n greater than or equal to 0. And we assume that this is true for that arbitrary integer n greater than or equal to 0. So in other words, our induction hypothesis is going to be that given any finite set with cardinality n, its power set is finite and has cardinality 2 to the n. Now we want to prove that this statement is true for n plus 1. So we want to prove given any finite set A with cardinality n plus 1, the power set of A is finite and has cardinality 2 to the n plus 1. So to prove that, let's consider an arbitrary finite set A with cardinality n plus 1. From here, we want to show that the power set of A is finite and has cardinality 2 to the n plus 1. Now, since n plus 1 is greater than 0, the cardinality of A is greater than 0. So that tells us that A is not empty. And therefore, we can choose some element of A, say x naught. And now we consider the set A set minus x naught. We're going to call that set B. Well, since A is a finite set and x naught is an element of A, it follows that A set minus x naught is finite, and its cardinality is equal to the cardinality of A minus 1. Or in other words, the cardinality of this set is equal to n plus 1 minus 1, which is equal to n. So since B is finite with cardinality n, we can apply the induction hypothesis to it. Right? It follows that the power set of B is finite and has cardinality 2 to the power of n. Now remember, our whole goal is to show that the power set of A is finite and has cardinality 2 to the n plus 1. And clearly, the power set of B is a subset of the power set of A, right? Every subset of B is also a subset of A because B is a subset of A. And so because of that, well, since we expect power set of A to have 2 to the n plus 1 elements in it, and power set of B has 2 to the n elements in it, this means we're expecting power set of B to have half of the elements of the power set of A. So then the other half should come from everything that's in the power set of A, but not in the power set of B. So we're going to define the following set we define the set F to be power set of A set minus the power set of B. So we're expecting power set of A to have 2 to the n plus 1 elements in it, which means we're expecting power set of B to have half of the elements of power set of A. So the other half should come from F. And the way we're going to essentially show that is by exhibiting a bijection between these two sets, power set of B and F. Okay, so then what bijection would that be? Well, remember, power set of B consists of all subsets of A set minus x naught. Or in other words, it's every subset of A that doesn't contain x naught. Therefore, we're expecting F to be all subsets of A which do contain x naught. And so the bijection we should be considering here, or what we expect to be a bijection, is by taking each element of the power set of B and adjoining x naught to it. So the function we define is as follows. So we define a function g over the domain of power set of B. And what it does is, it takes each element of the power set of B and maps it to itself unioned with the singleton set of x naught. So what we're going to do is, we're going to prove that g is a function from the power set of B to F, and that it is in fact a bijection from the power set of B to F. And so that's what we are going to work through right now. So we're going to move back up to the top. So up here, I wrote down some notes that we had written down in our proof. So now, let's show that g is a function from the power set of B to F. To do that, we want to show for every set S in the power set of B, g of S is an element of F. So to prove that, let's let S be an arbitrary element of the power set of B. Well, in that case, S is a subset of B, or in other words, S is a subset of A set minus x naught, which is a subset of A. But also, let's note, since x naught is an element of A, the singleton set of x naught is a subset of A. So then, from these two facts, it follows that g of S is a subset of A. The reason why is because, notice, we know that g of S is precisely the union of S and the singleton set of x naught. So, since S is a subset of A and the singleton set of x naught is a subset of A, it follows that the union of these two sets must be a subset of A. Right, in general, the fact that we are applying here is, given any three sets A, B, and C, if A is a subset of C and B is a subset of C, it follows that the union of A and B is a subset of C. So that's really what we're applying here. So, since g of S is a subset of A, that tells us that g of S is an element of the power set of A. Now, since x naught is an element of the singleton set of x naught, it follows that x naught must be an element of the union of S and the singleton set of x naught. So x naught is an element of g of S. So because of that, there's no way that g of S could be a subset of A set minus x naught. Right? If g of S was a subset of A set minus x naught, it would follow, since x naught is an element of g of S, then x naught is an element of A set minus x naught, which means x naught is not an element of the singleton set of x naught, which is absurd. Right? Or in other words, g of S is not a subset of B. Therefore, g of S is not an element of the power set of B. So we see that g of S is an element of the power set of A, but not an element of the power set of B. Therefore, g of S is an element of power set of A set minus the power set of B, or in other words, G of S is an element of F. And so, that's it. We have shown if S is any element of the power set of B, it follows that G of S is an element of F. And therefore, G is a function from the power set of B to F. So now we're going to be showing that G is a bijection from the power set of B to F. And to show that, we're going to show that G is injective and surjective to F. So let's first show that G is injective. To prove G is injective, let's give ourselves two arbitrary elements of the power set of B, call them S1 and S2, and we will suppose that G of S1 is equal to G of S2. From here, we want to show that S1 is equal to S2. That will prove G is injective. Now, since G of S1 is equal to G of S2, that means we have the union of S1 and the singleton set of X0 is equal to the union of S2 and the singleton set of X0. Now, since S1 and S2 are elements of the power set of B, that means S1 and S2 are subsets of B. Or in other words, S1 and S2 are subsets of A set minus X0. And so because of that, there's no way that X0 could be an element of S1 or S2. Because if X0 was an element of S1, then X0 would be an element of A set minus X0. And therefore X0 would not be an element of the singleton set of X0, which is absurd. So yeah, X0 can't be an element of these two sets. And that tells us that S1 and the singleton set of X0 are disjoint, S2 and the singleton set of X0 are disjoint. But then, with the union of these two sets being equal, and the intersection of these sets being the empty set, or in other words, these pairs of sets being disjoint, it follows that S1 and S2 are equal. The reason why is because of the following result. If we're given three sets, A, B, and C, and we have that the union of A and C is equal to the union of B and C, and we have A and C are disjoint, B and C are disjoint, it follows that A is equal to B. Right, so we're applying this result to the situation we have in our proof. Right, since the union of S1 and the singleton set of X0 is equal to the union of S2 and the singleton set of X0, and since these pairs of sets are disjoint, these pairs of sets are disjoint, it will follow by this result that S1 is equal to S2. And so that proves G is injective. Now we are going to prove that G is surjective. Now to prove that G is surjective to F, that means we want to prove for every element T in F, there exists an element S in the power set of B, such that G of S is equal to T. So to prove that, let's give ourselves an arbitrary element T in F. From here, we want to find an element S in the power set of B, such that G of S is equal to T. So then how do we come up with that element S that we send into G to give us T? Well, remember what G does. G takes every element of the power set of B and adjoins X0 to it. So if we want to figure out what element in the power set of B we adjoin X0 to give us T, well, we could think of that as though we take T and remove X0 away from it. If we send that into the function G, we're just adjoining X0 back onto it, and that will give us T. So our claim is, if we can send T set minus X0 into the function G, its output value will give us T. So let's first show that T set minus X0 is an element of the power set of B. Well, to show that, since T is an element of F, that tells us T is an element of the power set of A, but not an element of the power set of B. So one of the things we know is that T is an element of the power set of A. So in other words, T is a subset of A. But then since T is a subset of A, that implies T set minus x naught is a subset of A set minus x naught. Right? The fact that we are applying to go from here to here is the following. If we're given A is a subset of B, that implies A set minus C is a subset of B set minus C in general. So because T is a subset of A, that gives us T set minus x naught is a subset of A set minus x naught. Or in other words, T set minus x naught is a subset of B, and therefore T set minus x naught is an element of the power set of B. So this shows that T set minus x naught is an element of the power set of B, and so we can send T set minus x naught into the function g. So now we want to show that its output value is precisely T. And to show that, well, since T is an element of F, we also know that T is not an element of the power set of B. Or in other words, T is not a subset of B, or in other words, T is not a subset of A set minus x naught. So because T is a subset of A, but T is not a subset of A set minus x naught, it will follow that x naught has to be an element of T. And the reason why is because, well, what happens if we assume x naught isn't an element of T? Well, then in that case, we could prove that T is a subset of A set minus x naught, which gives us a contradiction. So to prove that, let's let y be an arbitrary element of T. Well, since T is a subset of A, it follows that y is an element of A. But since y is an element of T and x naught isn't an element of T, y cannot be equal to x naught. So since y is not equal to x naught, y is not an element of the singleton set of x naught. So since y is an element of A and y is not an element of the singleton set of x naught, that implies y is an element of A set minus the singleton set of x naught. So what we have shown here is, given an arbitrary element of T, it follows that it's an element of A set minus x naught, and therefore T is a subset of A set minus x naught. This contradicts that T is not a subset of A set minus x naught. So our assumption that x naught isn't an element of T leads us to a contradiction, so we must instead have that x naught is an element of T. And so the singleton set of x naught is a subset of T. And so it's because of this that it's going to follow if we send T set minus x naught into the function g, its output value will be T. The reason why is because we will use the following result. Given any two sets A and B, B is a subset of A if and only if the union of A set minus B and B is equal to A. So here's what's going to happen if we send T set minus x naught into the function g. By definition of g, this is equal to T set minus x naught union x naught. But as the singleton set of x naught is a subset of T, it follows from the result we have up here that this is just equal to T. And so that's it. We're done. We have shown, given any element T in F, there exists an element of the power set of B, such that if we send it into the function g, its output value is T. This proves that g is surjective to F. And so that tells us that g is a bijection from the power set of B to F. So we have shown that there is a bijection from the power set of B to F. So, since the power set of B is finite, it follows that F is finite as well, with the same cardinality as the power set of B. And remember, the cardinality of the power set of b is equal to 2 to the n. So the cardinality of both of these sets is 2 to the n. But also, since every element of f is not an element of the power set of b, it follows that power set of b and f are disjoint. So since f is finite, power set of b is finite, and the two sets are disjoint, it follows that their union is finite. And the cardinality of the union of f and the power set of b is equal to the cardinality of f plus the cardinality of the power set of b. But remember, the cardinality of these two sets is precisely 2 to the n. So this is just equal to 2 to the n plus 2 to the n, or in other words, we're doing 2 times 2 to the n. And 2 times 2 to the n is just 2 to the n plus 1. But the claim is that the union of f and the power set of b is precisely the power set of a. And that's just going to come from the fact that power set of b is a subset of the power set of a. First of all, this is pretty clear, because if we let S be an arbitrary element of the power set of b, that means S is a subset of b. And since b is a subset of a, follows that S is a subset of a, or in other words, S is an element of the power set of a. So since the power set of b is a subset of the power set of a, well then, when we do F union power set of b, well, F is precisely the power set of a set minus the power set of b. So if we consider the union of these two sets, well, since power set of b is a subset of the power set of a, we apply this result, and we obtain that this is precisely equal to the power set of a. So that shows that the union of f and the power set of b is equal to the power set of a. So this is really saying that power set of a is finite, and its cardinality is 2 to the n plus 1. But that was the whole goal of the induction step. So this closes the induction. So by mathematical induction, we have proven for every integer n greater than or equal to 0, we have, for every finite set A with cardinality n, the power set of A is finite and has cardinality 2 to the power of n. So we have proven the theorem. So this completes the proof. And so yeah, that's pretty much it for this video.